welcome to Nano. Today I'm going to learn a little bit about data tables.
We have our entries already set up with some docking results that we have here, along with some metadata that includes, some bioassay results on these molecules. And we have our protein of interest that's already co-crystallized with its magenta ligand here, gefitinib for all you that are interested. And we're going to start off with data table. So we're going to get data table out by going to the stacks menu. You can scroll down to here. The plugins are alphabetical, so it's easy to find. And I'm just going to click run. And what this will do is it'll pop up my web browser and give me, a data table to start from. And as long as Simon's willing to open up his web browser, I can click on this button right here, this square with the arrow. And you can't see that I've selected Simon here, but I'm going to select Simon. And I'm going to send him the same URL. And now he can open up the data table for himself.
Okay, so I'm just going to share my web browser. I just had this pop-up come in. And what I'm going to do is go to docking results and load it up. I think we've got everything we need
Excellent.
here. Perfect.
Looks
And
great.
you generated these results into a multi-mode SDF file. So it's just a standard kind of data
Yes.
format file. And yeah, just loading it in via the entry menu before we started.
Yeah, and so one thing, we're just going to check out settings here for Simon. So right now, he has a whole bunch of columns, showing. If he goes into the show columns section on the settings, he's going to be able to easily, he could scroll back and forth and run around, but if there's just a few that he's most interested in to discuss, if he goes into toggle columns, my favorite thing to do is just select all and deselect all, and then just you look through your list and you grab the ones that you're most interested in. And, I'll leave that up to Simon for what he likes for this discussion.
I'm going to go for log P versus maximized affinity as I kind of think that those
sounds absolutely fantastic. Great. So from here, this is a fun part. So in Nanome, I'm the presenter, so I can grab and move this protein around, but with the data table, Simon's going to be able to look at these molecules and decide which ones he wants to talk about and evaluate, as well as he can, if he doesn't want to go searching and scrolling, if he just wants the top minimized affinity, he's got a nice easy button here. Boom, we have our best, minimized affinity. Or he can go by log, or he can filter with the funnel. If he knows, well, I want the best minimized affinity, but it has to be a log below 5.
Okay, so I could actually have an incredibly
things.
So I could have a really large data set here, and then actually just start refining down, and then that's really cool, actually.
Yeah.
So with this kind of setting, obviously I'm doing this in XR with you, but we can obviously share this with people outside of a live session, and as long as they've got the short code that comes at the end of this, the session of the data table can be shared, which is kind of volatile, and once the session's closed, this data table will close down. So you don't actually have to even be in this space. We could just share this to our colleagues that are on their laptops.
Absolutely. And one of the fun things with that, so right now we can see these different molecules here, and classic thing from a docking result, being able to see this here. So pick any of these, ligands that you think are interesting to look at. And we're just going to take a look at it in the pocket. And if he clicks on it, he'll see that it highlights here in the table, and we can see that it's showing here. And now, the classic thing, if we take a look at this together, we're going to notice, you know what? This ring is kind of coming in close to gefitinib's halogenated ring. What if we want to throw some halogens on it?
Okay, then. So from this point, let's say we want to make some edits to the ligands. Can you take me through how I could do that?
Yeah, let's just start with our best docked molecule here, docking result 19. If we select this, we can look at it in the pocket. And we can see here, it's gorgeous. We have some really nice overlap with our co-crystallized ligand. We have a great hinge interaction. I'm really happy with this, but what's odd about it is while it looks a lot like our original, it's missing the chlorine coming off here. Maybe that seems like an obvious, easy edit. Let's go ahead and click on the pencil to the far left, and it's really easy just to add that chlorine in from here. even though you're not the presenter. Normally, it would require me to do it, but Simon can easily make a little addition without asking me to do this.
I think cool.
And
Yeah,
yeah.
I think it's going to come off around there, isn't it? That's the one.
Yeah.
Let's add that in.
Either meta position, yeah.
Okay, so I've put that in, and let's just use this button here to clean the structure up. Cool.
Beautiful.
And if I now save that. Perfect.
All right.
Awesome.
So
it's given me a log P I can see immediately.
that's the great thing. So here, if we go into settings, we'll show the secret behind that. So in our settings, we have a number of AutoCalc properties. Right now, we're using RDKit because that's just the open source tool that Nanome uses for, general usage. But if you have your own chemical properties calculator, these can happen live. Now, the docking results, obviously, this isn't a docked molecule, so we can't just invent that number. But we can always bring in any calculated property. And now that I have our molecule here, we can kind of take a look at what it looks like to superimpose a bit of this and take a look at it here in Nano.
I got it in the wrong position.
Well, to be fair, I think you did fine. I'm going to bring up the torsion tool, and we can always flip this around to get it in the right position.
Perfect.
And do a little overlay, get it a little bit more to the... I'm just going to do this. We'll do this angle. And we could use real-time scoring, or we could redock this molecule back in and see, how this compares to the one that's just fluorinated in the pocket. But one other thing I'll just mention here is if I bring up the entry lists, the way that we can find these molecules rather quickly is in the entry list, we have a special naming convention for molecules designed in the data table. VNM, we say Venom just for fun, but it stands for Virtual Nanomolecule. And it's just letting you, this is the very first one. So if you do design a bunch of molecules in Nanome, it's really easy to select them, go to export, make sure you choose SD file, and you can send this wherever you like. You can put it into Vault, you can send it to, whatever directory you're interested in that you're connected to. So you can always get these results. It's not just something you do in Nanome. Really easy to push it into any other application you're using.
Great. I mean, that's that makes it a nice way of doing sort of a light version of obviously the MedChem tool, and then I'm going to do some drawing and then have that automatically add to a data set. I guess what would be nice to show now would be maybe a bit about how you can graphically represent more complex data sets in Nanome and kind of find some regions of chemical interest.
Oh man, I love that idea. So this group that I put in here is very intentionally a decently diverse set of all the EGFR, antagonists that, are in the Kimball database. And so all of these have, some amount of bioassay data and some papers and stuff you can read. But what's fun about it is we did specify for high levels of diversity in the scaffold. So if we wanted to, we can go into show graphs here. And what we can do is we can go into the X and Y axis, and we can do, docking score versus ligand efficiency, binding efficiency, PIC 50, whatever sounds like, the most relevant piece of data for what we're interested in. We can graph them, compare them against each other. And if you scroll a little bit to the right, we can make this a bigger graph so we can see the whole thing more easily. Yeah. Perfect. And
Great,
now
so
we can see a lot of things.
So we're already highlighted on this one down here where we've got a fairly low binding efficiency, but a good maximized efficiency. Let's go right to the opposite end of the chemical space, shall we?
I love it.
What's the opposite? So if I click on this twice with my laser, it should highlight it. And oh yeah, I can see why that would be very different.
Yeah, so ironically, because of the search primers I did for high levels of diversity, this is actually what's known as a type 2 inhibitor. So it's actually supposed to bind a very different conformation of our protein. And so this one obviously docked as well as it could and looks like the way it did, but it's just a much bigger molecule, which, generally is going to change a bit of how it goes in. and it's based off of the maximized data point, which won't match our minimized affinity. So this goes to a different protein structure. So we're going to be able to see pretty easily the apples and oranges over here and see where the minimized affinity doesn't line up well with some of these other values.
Okay, I'm going to pick another one, and yeah, but we'll see what that looks like. I'm just going to pick one right in the middle here. Let's have a quick look down here.
Ooh.
Oh, that one's a tiny one.
Oh, this one's
Okay.
kind of fun though. Like, so what we can see here is it's just it's a very simplified kind of view here. And so I'm just going to yeah, so what we can see here, I'm just going to hide our ribbon real quickly just to kind of make it a little bit easier for us to see. 1 second. So what we have here, if we take a look at it and we look at the overlay, we can see that this initial part of the scaffold, this central ring structure, is actually the same on both. And this one is another one where we don't have the halogenation. And so we kind of found in this middle is we found something that has a great hinge interaction, a really easy dock that has, a good interaction right there. But it doesn't really have a lot of the other features that make it a capable binder. So it's great for docking, but obviously we're always going to have that discrepancy between binding and docking. And it's really interesting to see if we check some of the other middle ones. I'd be interested to see if we see a trend in having things there.
I think what I'd like to see as well is I'd like to know the log P of this one we got selected. So I can now just go from this and select log P here, and it should be highlighted down here.
Yeah. If you double click again, you can always, as you saw, you can see the value for that data point. You can see the exact value for both.
Okay, so let's find something that has a really low log P here. Something that there we go. So this is a fairly low binding efficiency. Okay, this is interesting.
Yeah.
I mean, we've already now just transversed a fairly complex data set in about 2 or 3 different ways within seconds. And we can do this both in and out of VR. And you don't have to have the Nanome desktop app to do this. Obviously, you can just literally have a web browser open and be on a Teams call and have someone on the outside just doing some doodling in the actual drawing component and updating what people are seeing in a live session, which is pretty neat.
Well, and the other cool thing to do, because you even mentioned how we started with this larger data set. Now, obviously, this is about 30 molecules. That's not a real large data set, but let's say this was 500 molecules or something much larger. What's really cool about this graph is we can see, look at this delineation. We can see that log P4 seems to be a bit of a line here. What if we wanted to do a deeper analysis on our less than and greater than log P4? And we can easily break this up into 2 data sets. And instead of looking at the whole thing all at once, we can try to look for trends in each set and see what we're able to see. So if we leave the graph, what we can do is, we can hide graphs here.
Let's go filter, I'm assuming.
Yeah, we'll do filter less than 4. And then we have a beautiful apply, the hidden hero. If we go to selection mode now, I'm a big fan of this. We're just going to select all. So this will only select the ones that are within the filter. And now we can duplicate. We want to do that as a single entry. Just so that's, not going to make it really difficult to sort through. And we can swap our entry from the whole data set. We can deselect all. Actually, let's do a refresh real fast. We'll do a refresh, and then we'll select our new docking results.
That's going to be the virtual nanomolecule 0001 bracket 1, right?
Yes.
Cool. There we go.
So now we've got our new smaller data set. We can see which entry it's in based on what's right there. And if we go in and we do the same binding efficiency by log P, we're going to see that we have, roughly half the results. And now we can take a deeper look at, look how much easier it is to see some of these clusters now that we're really focused on just one part of the scale. We can
Cool.
look
I
for
mean,
some different relationships.
that's pretty amazing. And obviously, we're doing this as 2 people, but we could have 3 or 4 people all doing different operations at the same time,
Well,
generating different candidates.
and what's fun is, so I'm gonna switch to the. I'm going to kind of look at this at the same time, and you'll see I'm in the same data set as Simon. But if I wanted to, I can go back to the original document results. Maybe I think, oh, that's really interesting, but I feel like there's something else there. We can always kind of resync and go back together and make sure that we're still interacting easily. But my graphs are also independent. And I can, instead of doing the same ones, binding efficiency and log P, maybe I'm like, I want to look at PIC50 and I want to look at the minimized affinity here. It's really easy for me to find something new. And I could do it while it's not visible to not make too much noise. But if I ever want Simon to see, like, hey, look at this, we have a really interesting, thing that's very much overperforming. Its PIC50 is great, but the minimized affinity is really low. Maybe this is just not the best model to consider. Maybe we need to try doing something a little different. Or I find something that's really consistent of where its PIC50 is low and the overall minimized affinity is low. I can see which ones are agreeing with our thoughts. So it's really great to be able to work asynchronously but come back together really easily.
Fantastic. I guess we're almost out of time, but could you really quickly take us through how you can actually look at some of this metadata in Nanome without using the data table, and kind of what the extra value is compared to using the advanced menu?
Absolutely. So one thing, once we were to make a pared down set of document results, we have these here that we really like. And we have like an idea. We want to look at our low log P set. Now we're on a much more manageable data set. In the advanced menu, it's really easy to toggle through and kind of do the same ranking as we used to do before. So this one here, that's a 1 star. I'm not very interested in this one. It's a type 2 and a type 1 model. That's not useful. This one's okay. It might not be the best, but it's definitely the right idea. And I can go through and do the same with a few others. Oh, that's a 5. That's really fitting in nicely. And now if we go back, we can once again keep all this data together, but I like the advanced menu for just flipping through easily. But when I have a large data set, it's best to handle it in data table to get your thoughts clear. And then, you can dig down into a smaller set, something like 20 or below. That's pretty manageable.
Fantastic. I think that's covered everything we wanted to with the data table. And thank you very much for setting up the data set and taking us through it. And hopefully anyone watching this will have a chance to sort of try this themselves. But if you have any questions or you have any data sets you'd like to visualize with us, drop us an email. We're always looking for interesting case studies to work on. And if you have a headset and you've got a temporary license with Nanome, and you want to see some of this within your scientific process, again, just drop us an email, contact us on Twitter, whatever the best way of doing it is for you, and we'll be in touch.
All right. Well, thank you, Simon. It was a pleasure. And hope to see you all in Nanome soon.
Perfect. Cheers, John. Bye for now.